Hello everybody, I am Thomas Kumar, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. So we'll continue with the lecture on vector calculus under the Module 1 of Applied Electromagnetic Theory. The topics covered under this lecture are differential length, area and volume, and the operations with bell operator, that is gradient, divergence, curl, and about solenoidal and irrotational vector. So when you consider any structures, it is made up of a number of small similar structures. So we are going for the concept of differential length, area, volume. So we'll take infinitesimally small lengths, then extrapolate them to the larger lengths. So if we consider this cubical structure, it is a small cuboid from the large cuboid we have. It is having side lengths dx, dy and dz. And if you integrate over the entire limit of the x, y and z, we'll get the entire cuboid. So if you consider this vector dl, so dl is a combination of displacements along x, y and z. That is, we will move dx units along x direction, dy units along y direction. So the differential displacement vector can be written as dx ax cap plus dy ay cap, and then we'll be moving dz units along z dash plus dz az cap. So this is the differential displacement vector in Cartesian coordinate system. That is, if we want to move from one point, that is, it is a vector which denotes the position vector of a point in Cartesian coordinate system. Now, when you consider the differential area, that is, the cubical structure has got total six faces, and if you consider the six faces, the area of the opposite faces will be equal, but the direction of the area vector, surface area vector, will be opposite to one another. So if you consider the top face is having sides dx and dy. If we consider the sides as dx and dy, the area vector is in the upward direction. So the area vector is dx dy. That is, area of a rectangle is dx into dy, and the vector is in the z direction. So ds, surface area along the z direction, is dx dy az cap. Now, if we consider the right face, it is having sides dx and dz. So the area of this side face is dx into dz, and it is in this direction, that is out of the rectangular face. So it is in the y direction. So it is dx dz into ay cap. Now when you consider the x direction, this is the front face. The sides are dy and dz. So it's dy into dz into ax cap. Now, if we consider the bottom face, the area vector will be in the opposite direction, that is the downward direction. So, the direction, it will be minus az cap. So, if depending on the direction of the area vector, it will be either plus or minus. Now, if we consider the volume of this cuboid structure, it is dx, dy, dz. So when you consider the volume, it is a scalar parameter, but displacement and area corresponds to a vector parameter. And this figure shows the three areas which is taken out from the entire cuboid structure. So when you consider in cylindrical coordinate system, the three coordinates are rho, phi and z. The differential displacement corresponding to the three coordinates are d rho and dz corresponding to rho and z because they are measured in length. But when you consider the phi, it is an angular displacement. So the length corresponding to the angular displacement of d phi, we should find it. So if we are having a radius rho, a sector angle of d phi, then the differential displacement is given by rho into d phi. Thus, the three differential displacements are d rho, rho d phi and dz. Thus, the differential displacement vector is given by d rho a rho cap plus rho d phi a phi cap plus dz az cap. Now, when you consider this figure, we are having a structure A, B, Q, P, D, C, I, R, S. This structure shows our differential lengths. This is a d rho, which is a small portion of the radius rho. dz is a small portion of the height of the cylinder, and rho d phi is a small portion along the phi displacement. Now, when you consider the structures, very small structure, so we can consider it as a small cuboid which is having equal area for the opposite faces. So totally it has got 6 faces. So we can find the area of each face. So if you are finding the area along rho direction, this is our rho direction. So we need to consider the face A, B, Q, P. So the sides are rho d phi and dz. So the area is given by rho d phi dz, and the area is in the outward direction, so it is in the arrow cap direction. Now when you consider the phi direction, so this is a phi cap. So you need to find the area of the face A, B, C, D. So when you consider A, B, C, D, the sides are d rho and dz. So the area is d rho dz A phi cap. Now, similarly, when you consider the z direction, z vector is in the upward direction, so we need to consider the face BAPS. So the sides are d rho and rho d phi. So when you multiply them, so we'll get it as rho d phi, and the vector will be in the AZ cap direction. So if you consider the opposite faces to it, it will be having a negative sign. Now, the shortcut to find the area vectors are, if you're finding the area along rho direction, you need to multiply the displacements along phi and z direction. So, if you multiply displacement along phi and z, it is rho d phi dz. So, you'll get the area along rho. Similarly, if you want to find the area along phi, it will multiply along rho and z. So, you'll get it as d rho dz a phi cap. So thus we have got the areas along the 3 directions in cylindrical coordinate system. And to find the volume, since it is a small cuboid approximated structure, we can multiply the length, breadth and the height. So we will get it as rho d phi dz. Thus we have derived the differential length, area and volume in cylindrical coordinate system. Coming to spherical coordinate system, the 3 coordinates are r, theta and phi. So r is already in length, so the differential distance can be given as dr. But theta and phi correspond to an angular displacement, so we need to find the corresponding length equivalent for the angle. So when you consider this figure, we are having radius r for the sphere. The angular displacement from the z-axis is given by theta, and the angle measured from x-axis in the xy plane is given by phi. So if you consider the small structure, the small portion along the radius is given by dr. And this is our angle d phi, because we are moving along the phi direction. A small angular displacement is given by d phi. When you consider small angle along the theta direction, you can get d theta. Now our aim is to find the corresponding displacement along theta and phi direction. So when you consider the phi direction, the same as the phi in cylindrical coordinate system. So when you consider the cylindrical coordinate system, the differential displacement, it was this length, and it is same as the radius of this sector into d phi. So as you all know, the radius of the cylinder was rho, so it is rho into d phi. So we will get this length as rho into d phi. So this length and this length is parallel to each other, so this is also rho d phi. As you have already studied, rho is same as r sin theta. So along phi direction, we will get the displacement as r sin theta d phi. Along phi direction, the displacement is r sin theta d phi. Now when you consider this small sector, this angle is d theta, and this radius is r. So the length of this arc corresponding to the radius r and angle d theta is given by r into d theta. Thus, the differential distance along the 3 directions is given by dr, r d theta and r sin theta d phi in spherical coordinate system. Thus, the differential displacement vector can be written as dl is equal to dr ar cap plus r d theta a theta cap plus r sin theta d phi a phi cap. This gives us the differential displacement vector. Now, to find the area, we need to multiply. That is, this is also considered approximately a small cuboid structure. So, it is also having 6 faces. Opposite faces are having the same area. So, if you are finding the area along each direction, so the radius is varying radially outward. So, if you find the area of this face, you will get the area along r direction. So, it is a product of r d theta and r sin theta d phi. So you will get it as r square sin theta d theta d phi ar cap. Now if you want to find the area along theta direction, so the theta is varying in this direction. So this is the a theta cap direction. So you need to find the product between dr and r sin theta d phi. That is, we need to find the area of the face in the back, or this is the one of the face. So it is r sin theta dr d phi a theta cap. Now if you are finding the area along phi direction, phi is varying in this direction. So if you are finding the area along phi direction, the two sides are r d theta and dr. That is, you will have one side as r d theta and the other side as dr. So you'll get it as r dr d theta a phi cap. Similar to the other case, if you multiply the coordinates along theta and phi direction, we'll get the area along r direction. If you multiply the coordinates along r and phi direction, you will get the area along theta direction. Now, to find the volume, you need to multiply the three quantities. So, you get it as r square sin theta dr d theta d phi. So, till now we have learned three main coordinate systems. One is Cartesian, one is cylindrical, and one is spherical. Now, I'll generalize the coordinate system to be UVW coordinate system, which is an orthogonal coordinate system with three coordinates U, V, W. The corresponding three unit vectors are AU cap, AV cap, and AW cap. Now, what we are going to do is that we'll define what is UVW if it is Cartesian, cylindrical, and spherical. So, if we consider Cartesian coordinate system, UVW corresponds to X, Y, and Z. For cylindrical coordinate system, UVW corresponds to rho, phi, and Z. And for spherical, it is r, theta, phi. Now here I have written H1, H2, H3. It corresponds to the factor that is to be multiplied with UVW so that we can convert angles into the corresponding length in displacement. Because if you want to convert an angle into displacement, you should multiply by some factor like rho or r sin theta or r. So here when you consider Cartesian coordinate system, all the three quantities are already in length. So we don't have to multiply anything else. So the multiplication factor is 1 in all the three cases. So when you consider cylindrical coordinate system, the three coordinates are rho, phi, and z. So when you consider rho and z, it is already in length. So you can multiply it with 1. But when you consider phi, if you want to convert a differential angle d phi into the length, you should multiply it with rho. So when you consider r in spherical, it is already in length. So we can multiply it with 1. Now when you consider theta, the corresponding length is r d theta. So we need to multiply by factor r. For phi, it is r sin theta. That is the same as rho. Rho is equal to r sin theta. So we will generalize the equation for differential displacement, area, and volume. So when you consider the differential length, it is, that is, we wrote for Cartesian as dx ax cap plus dy ay cap plus dz az cap. In general, you can multiply h1 with our differential length along u and the unit vector is au cap. The second one is h2 into dv av cap plus h3 into dw aw cap. So you can get the differential length in any coordinate system. Now if you want to find the area, in U, V and W direction. If you want to find the area along U direction, you will multiply H2, H3 with V, dV, dW and the area vector will be in the U direction. If you want to find the area in the V direction, we will multiply the things related to U and W. So it is du, dW, H1, H3 and the area will be in V direction. Similarly, in the W direction, it is du, dV, H1, H2 into AW. That is, whatever is the direction, the other things will be multiplied. Then we will get the area along the corresponding direction. If you want to find the volume, you will multiply everything together. So it is H1, H2, H3, du, dV, dW. Thus, this gives us the general equations for an orthogonal coordinate system. So now we have learned about vectors and certain properties of vectors. So now we will see the del operator, which is an operator which is applied on vectors. So the del operator in Cartesian coordinate system is given by ax cap into dou by dou x plus ay cap into dou by dou y plus az cap into dou by dou z. This operator is a vector quantity as well as it is having the derivative along the three coordinates. This is a differential operator which is applied to the vectors. And using this del operator, we can do a number of operations. And these operations are, one is gradient of a scalar, one is divergence of a vector, curl of a vector, and Laplacian of a scalar. That is, in general, we can denote a scalar quantity as V and a vector quantity as vector A. So del V is gradient of a scalar, del dot A is divergence of a vector, and del cross A is curl of a vector, del square V is Laplacian of a scalar. So these operations are the main operations which are done using the del operator. So now we'll see what are these operations and how can you do this. So now we have seen the del operator in Cartesian coordinate system. So in general, the del operator can be expressed as 1 by h1 au cap dou by dou u plus 1 by h2 av cap into dou by dou v plus 1 by h3 aw cap into dou by dou w. If you are considering Cartesian coordinate system, h1, h2, h3 was 1 and u, v, w was x, y, z. So this gives the expression in Cartesian coordinate system. Similarly, for cylindrical and spherical, if you substitute the corresponding h1, h2, h3 and u, v, w will get the corresponding expressions. So if it's study the general expression, you can get the expressions in the different coordinate systems. Now, the first operation using the del operator is gradient of a scalar. As we are having the scalar quantity and we are finding the gradient. So, gradient will denote the rate of change of a function because we are taking the derivative along each direction. So, it will denote the rate of change of a function and it is also a vector quantity, and this vector quantity will point in the direction of greatest change in the function. That is, in which direction the function will increase, in that direction the gradient will point. So it is denoted as grade V, which is equal to del V. V is a scalar quantity. So we'll take the derivative along each direction. In Cartesian coordinate system, it is given by dou V by dou x, Ax cap, plus dou V by dou y, Ay cap, plus dou V by dou z, Az cap. So when you observe the answer, it is also a vector quantity. And the properties related to gradient is that since it is a vector, it will be having a magnitude as well as a direction. So magnitude will be the maximum rate of change in the scalar quantity V per unit distance. And it will be in the direction in which there is the maximum rate of change in the function. And also, if the vector A is equal to del V, that is, if a vector can be expressed as a gradient of a scalar, then this V is called as the scalar potential of A. That is, it is a term, we'll see what is potential in detail later. So, if a vector can be expressed as a gradient of scalar, then that scalar parameter is called as scalar potential of the vector. Now, when you consider this figure, you can see white region and black region. So, white region corresponds to lower values and dark region corresponds to higher values. So, according to if you take the gradient of this scalar field, the gradient will be directed from outward to inward. That is, it will be directed from a lower value to higher value. Similarly, if you see in this figure, the white region is in this side, and as you move towards this side, it is turning dark. So the gradient will be pointed from this direction. So this is how we will get the direction of gradient, that is, it will point in the direction of greatest change. Similarly, you can see the general expression for gradient of a scalar, which is given by 1 by h1 dou v by dou u au cap plus 1 by h2 dou v by dou v av cap plus 1 by h3 dou v by dou w aw cap. Corresponding to the coordinate system, you can substitute u, v, w and h1, h2, h3. So in Cartesian, h1, h2, h3 is the 1. U, V, W corresponds to X, Y, and Z. So the expression for del V is given by dou V by dou X AX cap plus dou V by dou W AY cap plus dou V by dou Z AZ cap. Similarly, we get the expression in cylindrical as well as spherical coordinate system. So if you study the general expression for gradient, you can derive the expression in any coordinate system. The next operator using del operator is divergence of a vector. So before going into divergence, we'll see what is flux. The flux is the amount of a vector field which is passing through a certain surface. So the amount of flux passing through a surface will be dependent on the strength of the quantity. That is, if you consider the vector passing through it, it will depend on magnitude of the field, the size of the surface it is passing through, and the orientation. That is, if it is at an angle, then the amount of flux it passes through is less. And if it is on a flat surface, it will pass more flux. So divergence is actually, thus divergence is defined as the amount of flux entering or leaving a point, and it is defined using the equation. It is the amount of flux per unit volume as the volume swings about a point P. So when we consider divergence of A, it is the total flux passing through a surface S, that is A dot ds. We will consider the total value of flux coming out of a surface S per unit volume. So we'll divide it by del V, and this volume tends to 0. So when you consider this figure, here we are having a point P and all the flux lines are coming out of the point P. So we can conclude that it is having a positive divergence since all the field is diverging out of the point P. When you consider this figure, all the field lines are coming towards the point P. So we will tell it is having negative divergence. Now, when you consider this figure, the field is neither converging nor diverging to the point P. It is flowing in parallel. So, we will say that we are having zero divergence. So, these are the three cases in the case of divergence, and the answer for the divergence we will get is a scalar quantity. It will be either positive or negative. Depending on whether it is positive or negative, we can tell whether it is converging or diverging. So the general expression for divergence of a vector is given by 1 by h1, h2, h3 dou by dou u of h2, h3 into the magnitude along u direction plus dou by dou v h1, h3 into magnitude along v direction plus dou by dou w h1, h2 into magnitude in w direction. Similarly, we can get the expression in each coordinate system by substituting the value of u, v, w and h1, h2, h3. So this is the expression for divergence of a vector. So next we have got a theorem called as the divergence theorem. The divergence theorem states that the total outward flux of a vector field A through a closed surface S is equal to the volume integral of divergence of the vector A. It is applicable only for a volume which is enclosed by a closed surface S. And in terms of the equation, we can write it as closed integral S A dot ds is equal to integral over volume del dot A dv. So this is the divergence theorem. In one side, we are having a vector dot product with the area. On the other side, we are multiplying the divergence of the vector with the volume. So in problems, whichever is easy for us, we can use the corresponding expression. The next operation with the del operator is curl of a vector. So curl is denoting actually the rotation of a vector. If you consider a vector quantity and the amount of rotation is determined by the curl of a vector. So it is also called as a rotational vector, and the magnitude is the maximum circulation of the vector A per unit area, and it will be directed normal to the area. That is, if you are considering a vector field F around this, the curl is directed in the direction of maximum variation. So that is curl F, and it is given by closed integral L A dot dl. That is, this vector field A circulating around this region. So the amount of total circulation is given by A dot dl divided by the area as the area tends to 0. The maximum circulation is denoted by the curl and is directed in the normal direction. So that gives us the curl of a vector field. Now this delta S is bounded, that is, we'll have a closed region. So that is delta S is bounded by the curve L, and A and cap is the unit vector normal to the surface delta S. And this direction is determined using the right hand thumb rule. So the curl provides the maximum value of circulation of a field per unit area, and it is in the direction along which the maximum occurs. It will give us the amount of circulation about a particular point. Now when you consider this figure, here we are having a vector field around the point P. That means it is having a particular value of curl, and according to the right hand rule, the curl will be pointed out of the page. If you take the right hand thumb rule around this vector field, the curl will be pointed out of the page. But when you consider this figure, it doesn't have any rotation about the point P. Thus, it is having zero curl about the point P. That is, if it has a rotation, it will have a curl, and if the vector is not having any rotational properties, then the curl will be equal to 0. In Cartesian coordinate system, we can determine curl using the expression of cross product. That is, it is the determinant of ax cap, ay cap, az cap. In the first row, we will be having the first order derivatives. That is dou by dou x, dou by dou y, dou by dou z. And in the second row, we will be having ax, ay, az. That is the magnitude along each direction. So as you can observe from this, the answer will also be a vector quantity. So the curl of a vector quantity is another vector quantity. Earlier when we told about divergence, divergence was of a vector is a scalar, but curl of a vector is again a vector. Now when you take the divergence of curl of a vector field, it is a property, that is, if you take del cross A, it is the curl of a vector. Again, if you apply the divergence operator, it will be always equal to 0. And when you take the curl of a gradient of a scalar field, that is, gradient is del V. If you consider the curl of the gradient of scalar, that is del cross del V, it will also be equal to 0. So these are the properties which are related to curl of a vector. In general, the expression for curl of a vector is given by 1 by h1, h2, h3. Determinant of the directions are given by h1, au cap, h2, ab cap, h3, aw cap. Then we'll take the derivatives, that is dou by dou u, dou by dou v, dou by dou w. And in the last row, we'll be having h1 into magnitude along u direction, h2 into magnitude along v direction, h3 into magnitude along w direction. Similarly, we can substitute the values of h1, h2, h3 UVW corresponding to cylindrical and spherical coordinate system and get the expressions of curl of the vector in cylindrical and spherical coordinate system. Now, the next theorem related to curl of the vector is Stokes' theorem. And Stokes' theorem states that the curl of a vector field A around a closed path is equal to the surface integral of the curl of the vector A. Now, when you consider this closed path L, if we are having a vector field A, when we take the closed integral L A dot dl, it is same as finding the surface integral of curl of the vector A. That is, we are taking a small surface S along this open surface S. Along this ds, if you find the curl of the vector A and integrate it over the area S, we will get the same value. That is the Stokes' theorem. Now we'll try to illustrate the Stokes' theorem. So we have already seen the equation as closed integral L A dot dl. It is equal to integral over surface del cross A dot ds. So we are considering a closed path L where a vector field A is circulating around the closed path L. In order to prove this, we are dividing this closed path into a number of small paths L1, L2, etc. up to Lk. And along each path there is a circulation of the vector. That is, along this path there's a circulation, along this path there's a circulation, like that all the k path will have a circulation around it. So the closed integral A dot dl can be expressed as the summation over k, the integral over A dot dl over the k path. So it is, we'll take the integral over A dot dl over each path from L1 to Lk. So this closed integral A dot dl, we are multiplying and dividing by the area along each path k. So by delta sk we are dividing and multiplying it with delta sk. Now when you consider this equation, when you consider the path along the interior path, if you consider L1, the field is moving from bottom to top. When you consider L2, it is moving from top to bottom. So along the interior path, the fields will cancel out each other. So therefore, the sum of the line integrals over Lk, it will be same as taking the curl around the closed path L. Therefore, this term reduces to what is called as the curl, which is del cross A. It is because when we take the integral over Lk and if we sum it over the entire path, the only thing which remains out is the outer lobe. That is why this entire term can be reduced to integral over S del cross A. And this area is tending towards 0. So that is why this is reduced to curl. So we'll get the expression for Stokes' theorem. Now we'll see two special types of vectors called as solenoidal and irrotational vector. Solenoidal vector is also called as divergence-less vector. So a vector A is said to be solenoidal if the divergence of the vector is equal to 0. That is, if del dot A is 0, it is called as a solenoidal vector. So when you consider a field which is solenoidal, del dot A is 0. So according to divergence theorem, closed integral S A dot ds is same as integral over volume del dot A dv. If del dot A is 0, we will get the value of closed integral S A dot ds as 0. That means the flux lines which are entering a surface, it should also leave it. That is, the net flux emitted by a closed surface S will be equal to 0. Therefore, this field A will be either a source nor a sink for flux, since the closed integral S A dot ds equal to 0. When we discussed the curl of the vector, we have already told that the divergence of the curl of a vector field is always equal to 0. Therefore, the field of curl of any vector is always solenoidal in nature. Now, when you consider solenoidal field, we already know that del dot A is 0. Also, we know that closed integral as A dot ds is 0. So when you compare this del dot A 0 and del dot del cross F 0, this A can be expressed as del cross F. That is, if a vector is solenoidal, that vector can be expressed as the curl of another vector field. That is the property of a solenoidal vector. Next is the irrotational vector. A vector is said to be irrotational if the curl of the vector is equal to 0. That is, if del cross A equal to 0, then it is said to be an irrotational vector. So according to Stokes' theorem, we already know that closed integral L A dot dl is same as integral over S del cross A dot ds. Since del cross A is 0, we will get closed integral L A dot dl as 0. That means if the vector is an irrotational vector, then the circulation of vector around the closed path is equal to 0. That is, irrespective of the path taken, the integral over an irrotational vector over a closed path is always equal to 0. So the vector whose line integral is independent of the path is called as a conservative field. One of the properties of the curl was the curl of the gradient of a scalar is always equal to 0. That is, the field of the gradient of a scalar is always an irrotational vector. On comparing this equation with our equation del cross A equal to 0, we will get A equal to del V, where V is called as the scalar potential of A and A is called as the potential field. Thus, from the property of an irrotational vector, we can express a vector as a gradient of a scalar. So now we have seen special types of vectors called as solenoidal and irrotational vector. So there can be cases where these condition can be satisfied or it can't be satisfied. So we'll see the different cases based on the value of divergence and curl. So the first type is in which both divergence and curl is equal to 0. That is, when you observe this figure, it is not diverging or converging to a point. Therefore, the divergence is 0. And when you observe, take any point, the vector is not rotating about that point. So the curl is also equal to 0. So this is an example for a solenoidal as well as an irrotational vector. The next case is the one in which the value of divergence is not equal to 0 but the value of curl is 0. So when you see this example, when you consider a point inside this, the field is diverging away from that point. That means it is having certain value of divergence. But when you consider a point at the center, it is not rotating. Therefore, the curl is equal to 0. So this vector is an field is an irrotational vector, but it is not solenoidal. And the next case is the value of divergence is equal to 0, but the value of curl is not equal to 0. That is, if you try to join these vector fields towards a point, it will not converge or diverge from a particular point. That means the value of divergence is equal to 0. But if you take any point, the field is rotating about it. That means the value of curl is not equal to 0. Therefore, this field is an example for a solenoidal vector, but it is not an irrotational vector. So the last case is both the value of divergence as well as curl is not equal to 0. So this gives an example for not a solenoidal and not an irrotational vector. That is, if you try to join these lines, it will converge at some point. That means it is having certain value of divergence and certain value of curl since it is inclined at an angle and it is rotating about it. So these are the four types of vector field. That is, if you consider any vector, it will fall into any one of these categories. So we can conclude this lecture on vector calculus. We have discussed about differential length, area and volume, different operations using del operator like gradient, divergence and curve, special types of vectors like solenoidal and irrotational vector. Thank you.